And so we're gonna do some physics with balloons. So let's inflate a balloon and release it. So the reason why a balloon kind of flies around faster at the end is the same reason why it is much harder when you start inflating it to blow it up than once it's much larger, right? Okay, so what's going on here? So the pressure inside a balloon is much greater in the beginning. It really drops as the radius of the balloon increases. And this might be a little counterintuitive, but it actually does make sense. So there's a couple of things happening here. On the outside, you have the atmospheric pressure that's trying to crush the balloon in, and you also have elastic surface tension from the balloon that's trying to kind of shrink it in as well. And on the inside, you need to have larger pressure than the atmospheric pressure in order to balance that that inward force, right? Okay. So when the balloon is very tiny, okay, the forces on the outside that are crushing it in, the atmospheric pressure and the tension, the rubber, are similar to the ones later, but the area of the balloon is much smaller. So that force being applied to a much smaller area makes the pressure that needs to be balanced much larger when the balloon is tiny. One thing you can notice that if you drop two balloons, one inflated more than the other one, see what happens. Okay, so more inflated balloon seems a little more buoyant. So the reason why a larger volume balloon is more floaty or more buoyant is that it having a larger volume and not having significantly more mass in it spreads out the mass throughout, so the density of a larger balloon is much less. Now let's see what happens if you pop a small and a large balloon. Is the sound the same? Big difference there, right? Why do you think so? What we have here is a balloon full of water and one with air, and we're gonna pop them and see what happens in slow-mo. Okay, so I have here is two balloons. One is inflated a little bit, the other one is more inflated, and they're connected with a tube. And I'm gonna let go. What do you think is gonna happen? Which way is the air gonna go? I'm gonna untie them so that they can breathe each other's air. Oh, see what happened? The little balloon actually gave its air to the larger one. Did you expect that? That's because the pressure in the small balloon is much greater due to its much smaller area, and the larger the balloon gets, the pressure gets lower, which is why it's much easier once the balloon gets larger to keep blowing it up. Here is a balloon full of water, and we're gonna pop it to demonstrate Newton's law of inertia, how the water would keep staying there even after the balloon is removed. Here's another thing you can do with the balloon for action reaction and kind of to show how the gases are coming out when you let go. This is full of water. Use an inflated balloon as an example of energy conservation. When you're inflating it, you're giving it elastic potential energy, and when you let go, that's converted to kinetic energy motion. Pay attention to the pitch of the sound when I let the balloon open. Pay attention to the pitch of the sound from a larger balloon. We have a higher pitch for a smaller balloon and lower pitch for a larger balloon. And that shows you that the flapping at the end of the rubber that's actually making the sound is flapping much faster for a smaller balloon because the pressure is greater.